Okay, so we will look into now parametric approximations. It includes cost function approximation and policy approximation as well. And approximations involve kind of feature extraction, and then we can see this as two-step process. So extract the features and then do the approximation, or it could be done in one shot. So we will see that. So in general, we can see this as a scheme that that is illustrated here. So we can have some samples, and then these we apply the usual we have the states, I mean, and we apply the usual rollouts, and then from there we have some control choices, and then these pairs, the state and then the control, it goes through these nonlinear or neural network based architectures. So let's say we want to approximate in the policy space, then we need the state and the control. So these pairs goes in, and then we can build a neural network architecture that will fit this training data. So given a state, what is the control we are supposed to take? So that's the data we have, and then we may build a least square classifier that tells us which of these controls to pick, and this allows us to replace the policy that we had before. Okay, so the base policy that we had before. So this is a high level diagram, and the more details of this we will see now. So let us see parametric cost approximation first. So in the cost approximation, basically we want to approximate, we want to approximate the cost, but we want to do it parametric approximation of the cost. So here, unlike the previous example, here we are looking at cost function approximation. So we need state and the corresponding cost as the label. So here our training data set is like X and JS. Okay, so let us say these many samples, Q samples you have. So this is the training data, and it goes in the approximation architecture, and this approximation architecture gives me an approximate cost estimation, which is J tilde, right? We call it tilde because it's an approximation, and for various values of R, we get certain approximation of this cost. So in the cost space, we can again have this parametric cost, where the target cost Jx is approximated by J tilde x R, where R is the parameter. So these are weights of neural network, and obviously this depends on parameter R, and the training data, as we discussed, it's xj. Okay, and there are Q training samples, and then we would like to find a parameter R hat that minimizes this error for each samples. Okay, so we can build this training data, and not just that, we kind of fit a parametric function on this training data. Okay, and so it may happen that you may compute these costs in some other way. Let's say, so for a given state, you have, let us say for this one you have some jx1, for another cost you have jx2, and so on, xn you have jxn. You may have this cost estimations via some other approach as well, but the whole point is you generate this data. Okay, and then the idea here is that the state space can be very huge, so there could be some intermediate state here, let us say x2 tilde, which was not really seen in this training data, but it is kind of, let us say, close to one of the existing states. Okay, so that's where these this prediction function will help, where it will help you to predict now cheaply the cost for this x2 tilde, which you may not have seen during training. But this x2 tilde may be kind of very close to something it has seen in the training data, and it will kind of interpolate and give you some approximation. So that's the whole idea about cost approximations, cost function approximation. The problems where you have the state space is very big, you may need a neural network to do these prediction tasks. Okay, so we get a basic idea of how we can do parametric approximation for cost. So as I said, we can do parametric approximations for the policy as well. So there are two ways to do parametric approximations. We can do it for the cost. We can see that the parameter is giving me a way to compute the cost, or I can see that my policy is has this parameter. So these are two different views. So I can see my policy function mu tilde as some parameterized function. So again, here also we can do if we want to do it in a policy approximation, then we can again collect data of the state and then the control that I'm going to take. So let us build a data here. So this will be state 1, and then the corresponding control will be given by let us say at x1, x2, then what was the control taken at x2, and so on. Now this becomes my training data. Here again the idea is very similar, that I may encounter a state, let us say xk tilde, for which I want a good guess of the control, and it may not have been in the training data before, but it may be very close to some xi, and for that the neural network will give me some prediction for xk tilde. Okay, depending on the pattern how xk is related to some of the states it has seen in the training data. It will give you a cheaper prediction of the control, cheaper or faster prediction of the control, especially if the control space is huge. Okay, so the same idea applies here in the policy space. So we can obtain training data from rollout control calculations. So how do you build this data? You do let's say a lot of rollouts. So we know that rollouts can generate a lot of these training data. So we can do it for both policy and value networks. Now what is the difference between cost function approximation and policy approximation? Like we have seen two ways we can do these approximations. Now when we look at the cost, then cost is a real number. Okay, so cost typically, unless there is a very special setting where cost is like very discrete, like either you get, let us say there is a game where the reward is given to you and reward is like only 10 of the rewards are there, or either you get those 10 rewards or you get a 0 reward. So in that case you can say that the cost, which is the reward, is discrete and finite, and maybe these are integers, 10 integers. But in general it's not like that. Costs are really usually some real number. Okay, and policies typically are, of course policy can also be continuous. For example, a robot moving along certain path, or a self-driving car. So we will see some examples of that. So of course control also could be into two different cases, where it may be continuous as well as discrete and finite. So in usual cases you will treat cost as real numbers. Then what does it mean for What does it mean for the approximation architecture? Well, for cost approximations, it will become a regression problem because our levels are kind of like real continuous data, and if our controls are discrete and finite, it becomes a classification problem where we assume that there are m controls and we are kind of trying to predict which is the best action to take out of these m possibilities classes. So this is something you have to decide. This is not a statement that is valid for all cases, but typically costs are real numbers. It will be a regression problem, and policy approximations will be a classification problem in general. So for example, it's typical to have control space U that consists of n m-dimensional vectors and consists of m numerical components. So for for continuous, in case control is also continuous, then obviously you have to go for regression there as well. Okay, so let us see some examples. Controls in self-driving car. Is it continuous or discrete? So what could be control in a self-driving car? Is the steering wheel. So basically in a car you are supposed to brake, or you are supposed to apply the brakes, or you are supposed to steer. So steering as such is a continuous thing. You don't do it in a discrete way. You don't do it like 10 degree, 20 degree, something like that. But on paper, it's like a continuous control. So you can say that since we will put this discrete data on a computer, then you can say that it's finite, because computers can only represent finitely many numbers. But the point here is that we consider a control to be continuous when it can take a range of values, but very large number of them. Okay, so otherwise, kind of many things are finite once we go and implement it on a computer. If it's a self-driving car, then typically you will have rotation angle. So typically you will go 0 to 30 degree, usually not lot more on a road, and it will take a range of values. You will allow as if it's like a real number. So you may allow maybe 10.5, 10.4 degrees, and so on. So we will say that this is a continuous control. And similarly, it goes for the brakes. Depending on how much pressure you put on the brakes, there is a wide range of values to consider when we apply brakes. So this in general here, the control seems to be, we can take this to be continuous. Same thing we can say for the billiards game. Here also we will treat this as continuous control, because if you play a computer game for billiards, then you will move this, and the amount of force that you will apply with this will depend on how much you move this back. Okay, so again, the range of possibilities for moving this billiard stick is like large number of possibilities are there. So hence we will again treat this as continuous. Here again, angle is also kind of lot of possibilities are there for the angle. So again, it's good to treat this as continuous. Control. Now here it depends, right? No, here we can say safely that it's finite. We can model this as kind of finite, because what are the controls I have in hand? Left, right, down, and rotate. So rotation is like 4. So each time it rotates 90 degree. So 4 rotations plus left, right, and down 3. There are 7 possibilities for control. So we will model this. If we want to use parametric approximations, the control is control will be a classifier. Control predictor will be a classifier. Okay, so this is what we said just now. The control space, if there are m controls, is finite, and then we have for any x, mu tilde xr consists of m possible possibilities. So there are m classes to predict. Now, as you know from machine learning, that you can you may use this softmax to predict among these m classes. So which is the best likely control to be taken? This could be predicted by softmax. Softmax gives you a probability out of these m controls. Softmax gives you the best, the most probable control to be taken at a given state x. And we call it randomized because of the fact that we use softmax. Because softmax gives me a distribution over the policies. There are m over the classes. So there are m classes. So it will tell me 0.9 or 90% you go with the control k, and then 80% go with if it's 90%, then remaining is like 10%. So maybe 5% go with some other, 2% go with something else, and so on. The usual classifications that you do. Okay, so all these tools that you know from machine learning, you can borrow and use this to build a approximation for the control. All right, so here we said randomized. Now randomized has some utility in the sense that using softmax allows me to use gradient based optimizers, because it's a differentiable function, right? So I don't want to build a classifier that gives me the max of these controls, because max is non-differentiable function, whereas softmax is a differentiable function. So sometimes randomized outcome is actually a good thing. It is not just useful for exploration point of view, because softmax is giving you some probability to explore some controls, but then since it's a probability, while sampling from this policy, you may sample some other action which is second likely. It will be rare, but there is a possibility. Yes.
Let's say
Gear is one of the many controls. No, it will when we are looking into randomized policies. Let's say, for example, with softmax, it may tell you the first gear or the second gear also. It is kind of telling you the most probable, or there is a possibility of second most probable. It will be very rare. It will be very rare that it will tell you fifth gear. You need first gear, let's say. So in the randomized settings, we see policies at transition functions. So this gives me most likely action that I will take, but it may also give me the second most likely, because it's kind of, I'm doing the sampling of actions from this distribution of action space or the control space, where I'm doing sampling, and this is during training. This is during training. Okay, I will come back to your answer. Now his question is, let's say I'm doing a self-driving car. Let's focus only on the gear, and gear I have, let's say, 5 gears, and in the situation I am in, let's say on a hill, I do want to use the first gear, and this is while I'm doing the training, and my policy I use is randomized. Then look, initially when you are training, you may even try the fifth one, right, in the very initial part, and you get a very bad reward. If the car goes down, it doesn't go up, maybe, so it will be very bad reward, and next time you will say no, that you will kind of improve on that policy. So maybe try something else, because overall your things were not good. Now let us say you trained a lot, and then in that scenario, what policy is learned is the best is like the best action to take is the first gear. but still it's a distribution. So there is a possibility 0. Let's say 2% or whatever, it will take second gear, and the possibility for others may be negligible or maybe 0 also. So it is possible that it goes for second gear, although it is very rare. I can change softmax to max during testing. During testing, I can say, look, I am done with training. I will always go with the max each time. So that way, randomized policy becomes a deterministic policy during test time. It's possible to do that, and this is in fact done very regularly. That you change your softmax to max, make it deterministic in a very critical cases. You don't want to take second chance, right? Like you always want to take the best each time, right? So you may do that. In fact, this is something I want to remark here. So that's a very good question. During training, you can do that. You keep increasing your policy is like a distribution. Force it to have very likely outcome as the first gear. Keep training, and at each state you keep training so that as a distribution, it gives you very likely outcome, which is the best outcome in that case. But since it's randomized, there is no harm in exploration also. So even if it gives me something which is the second best, it is part of exploration during training. So I don't mind. Even if it didn't give me first gear, it gave me second gear. Why should I mind? Let us see what happens with the second gear. Maybe I find something interesting with the second gear also. If second gear becomes the very good one, because the first gear it was not a requirement to have the first gear because the slope was not that steep. It was kind of medium, and second gear was good enough. We know that first gear is a bit costly because it will take more like power and cost petrol. So during training, if it explored and went for the second option, and I will see that my reward was good because let's say cost of petrol was less, or maybe the time to go there, because second gear is faster, the time to go there was lesser. Then the policy will the distribution will change around that state to second gear as most likely, then the first gear. So during training, working with a randomized policy is actually a good thing. Specifically, if you are at the final layer and you're looking at the softmax, is a good thing overall because training is also good. Okay, so there are two things. Exploration is also good with randomized, and training is possible with gradient descent or ascent, whatever we want to do. Okay, so this is, in fact, I have something for some comment on randomized versus non-randomized. Randomized policy mostly used during training. So because you also want to give a scope for explorations, right? So in that case, yeah. Whereas if you have deterministic policy, then obviously it's not. So basically, you are only exploiting in that case. So randomized policy helps in your explorations, can cause randomness in real world system. So during deployment, randomized policy is not good because it can create randomness. Let's say it's a surgery going on, and maybe in those critical cases, medical surgery, then the best thing to do is the only thing to do maybe. The second best is you don't want to take any chance. So in real world safety critical systems, you may want to get rid of randomized policy and you want to ensure consistency. Okay, so this is safety critical. So randomized not reliable. This guarantees safe execution. Look, safe execution, but again, if we use parametric network and so on, then even if we do the max from there, right? So there is still possibility that something might go wrong because the way it was trained and so on, the data it saw. But so guarantee may be a very strong word here, but it is certainly better than randomized policy, because here we are going for whatever best we could learn during training, and we are applying the best policy during deployment. We are not like taking second chance. At least from the training point of view, we are using the best knowledge we have. Still things can go wrong. So computational efficiency, it's more complex because in randomized policy you do these sampling steps. Sampling could be uniform, sampling could be priority is given in a certain way to certain set of states or actions, and so it depends. So here you also have to think about sampling. uniform may not be the good one all the time. Of course, here you don't think about sampling, it's deterministic, so you go very fast here. In optimization methods, it helps in gradient based approaches, so as I said just now. And for in a classical control problems, they use deterministic policy. So in classical control, like they are happy with deterministic policy anyway. Kind of they mix dynamical systems with this, so they are okay with that. It solves their problem. They don't need to be exploring randomized policy. But more and more they are also coming in this domain of randomized policies, because randomized policies also kind of gives you more robustness in some sense, because you may have some differential equations or something to kind of govern the movement of hand or the control of the hand or so on, but we know that it may not be robust when there are some external factors involved. So randomized policy also takes into account a few of those things where some external disturbances could be there. Okay, so a randomized policy is essential for learning, but a deterministic policy is ideal for real world decision making where consistency and safety are required. Can we convert randomized policy to non-randomized? So by now you already got the hint. Use the max. So there you go, you use the max. Here you are not supposed to do the training, so you kind of use the max here and kind of fix it. So right now during training, mu tilde was kind of your is kind of a distributions where you sample the actions, but here you are saying no, always go for max. No ambiguity. I don't want any ambiguity. Okay, so basically with max you convert a non-randomized policies to you convert a randomized policy to non-randomized. Okay, so cost function approximation. So let us look into some details. Like if you have done machine learning, then the remaining part will be kind of very easy for you. So if we look into cost function approximation, then as I said, we have a cost jk, xk, rk. R is the parameter, and this may be some parameter vector. So there are m of these parameter vectors, and this set of functions for various parameter r obviously gives me variety of functions to choose from. It's a class of functions. For different r, I get different class of approximation function here. So now what are the ways of parametric approximation? One thing I already told you is like neural network is like everyone prefers now for a complex cost calculations. So perform various ways. So maybe you can perform semi-exhaustive or semi-random search in the space of parameter vectors, and then you may look for parameters that yield the best performance, let's say with the one-step look ahead that you want to do. And this is only when your parameter count is like relatively small. You may use Bayesian optimization or random search to tune the hyperparameters. In case you are using neural network, then you know that number of layers and number of clusters are also decide the architecture that is used for approximation. So this is basically part of hyperparameter tuning. Other approaches could be the classical ones like least square approximations. So here again, the training set typically will consist of state control pairs, because we are looking into, let's say, value function approximation, and some kind of sampling process. It may be uniform, it may be some prioritized way to do the sampling. Okay. So the classical approximations that we know from numerical algorithms are polynomial based approximations, wavelets, Fourier basis. You can approximate functions via sine and cosine as the basis. Polynomials basically means that you want to approximate a function using basis like 1x, x square, x cube. So you are expecting that this f belongs to span of polynomial basis, right? So you do some linear combination of these polynomial features. So that's one possibility. So this f is our value function, and we may want to approximate it like this. You may use some interpolation schemes, and obviously the favorite is neural network now, right? And radial basis functions, if you are kind of aware of, then this goes into like numerical domain of numerical algorithms where there are so many possibilities to approximate a function. If the problem is simpler, then go for maybe polynomials. They are a very cheap one. Again, here you have to decide what degree polynomial you want to fit. So these are basic numerical algorithm schemes. So if you do linear approximations, then it is like this. You can see that the error is like this. If you went for maybe second order polynomial, then your approximation may be like this, because second order, so it can bend once. And in this case, maybe the error reduced a little bit compared to the previous one. And if you go for third order, then maybe like this, and it will be better than the second order, and so on. But the problem is the complexity is increasing now. The complexity increases because the polynomial, let's say the linear one will be span of C1 plus C2x. Polynomial of second degree will be C1 plus C2x plus C3x squared, and so on. So as you can see, if you want to fit a polynomial, then here the number of parameters you need are 2, C1 and C2, to identify this polynomial, and here the parameters that you need are C1, C2, C3. So there are 3 parameters to be estimated, and so on. So depending on the problem at hand, you may go for cheaper approximations or a more complicated approximations. If it is really very complicated, then always go for neural networks. Okay. So if we assume that we have some features extracted, here the feature, by feature we mean features of a state. Okay, so if we have some way to compute those features, let's say those features are phi k. So given a state xk, let's say the corresponding feature vector is phi k, right? And this feature vector length is mk. Okay, so let us say this feature vector length is mk. Now this state xk may be in a very high dimensional space, let us say like this, 1 million or something like that. And the whole idea is that this phi k xk is, let us say, very small dimensional space. In this case it's mk, and mk is much less than, let's say, this one, which is million, right? Now how did we extract these features? Well, I did not tell how did we do this, but let us assume we do it somehow. Then given a state, we extract certain features, and ideally those features should be much less than the state itself. Now once we do that, then the next step is to work with features and not with the state. So in other words, the approximation architecture J tilde is now only working with the features phi k xk, which we believe is like very small vector. So cost approximation depends on xk indirectly through the feature phi k xk, which is much easier to work with. Okay, so the reason why we use this phi k xk is that we believe that these features might also change, or the feature dimension might also change with the states. So for state xk, the feature function could be phi k, but if I go to xk plus 1, then even the way I extracted the features might change. So the process of extracting the features does not have to be stationary. It is allowed to change. Okay, so non-stationarity of the state space over time means that features can vary. Features can vary when we are dealing with non-stationarity of the state space over time. There are cases, for example, where you are driving the car on some plains, whereas sometimes you are driving the car on some icy roads. So there you may have a feature extractor that that may change because of the icy conditions. You may need some more extra information from the state. So those could be classified as non-stationary cases. But for many problems like games, ideally you will have a feature extractor that remains the same throughout. You don't really change your feature extractor. Okay, so so for a stationary problem, it's very common to use the same features throughout. So why do we do feature extraction? Well, one thing I told you already is that the state space can be very huge, and we may want to do some dimensionality reduction so that we can at least work with that reduced vector space. So it could be a computational thing. Okay, so let us see with an example. So I gave some of these hints before in my previous classes, but let us see in more detail in the papers what exactly they consider as features in Tetris game. So in Tetris game, when you play, do you remember all the states? Not really, because for you the states will be these long vector of ones or zero, and so on, and this indicates which of these is occupied, which of these is not occupied, and so on. So this, we have discussed this before as well. Which of these blocks are occupied? Let's say we call it 1, and the places which are not occupied, you treat this as a matrix. Let's say 1 1 1 2 and so on, and you can make this a vector like this. So this is the vector I'm talking about, and you can represent the states like this. But in a 100 times 50 Tetris board, the possibilities for these are 2 to the power 2 to the 5000. So as it happens, 2 to the 5000 is more than 10 to the 78. So which are atoms in the universe. So basically these are the motivations behind feature reduction. So when you play the Tetris game, what are you really looking at, right? So when you play the Tetris game, does your mind locate the gaps in the rows? Very likely. When you are playing, you will look at, when you are playing Tetris, then you cannot miss this spot, because this is your immediate reward that you are going to get, and this block that is coming from the top, very likely you are not going to miss this opportunity to put this block in this gap and get some rewards. So certainly you are looking at one of these features, which is this gap here, right? Does your mind look at the size of the region around the gaps? So maybe you're also worried about what is the height of these skyscrapers around this area. So if it was a slightly different problem, then the relative height could have been useful here. So for example, let us say this block was occupied, and let us say this block was not there. Let us say this block was not there. Then you will look at this area a lot more, because if you rotate this guy, then it will become like this, and if you put this here, let us assume that these blocks are not there, then it will fit right here. And let us assume that these blocks were not there. Then putting that block here, let's say these blocks were not there, or putting that block here, you will think about putting that block here compared to here, because here you see that you can have 2 rows filled if you put that block here. So in these cases, I am looking at relative heights of these columns as well, where I can complete the 2 rows and so on. So so these could be seen as features of the game, where relative height matters, where there are gaps, and so on. So all these things we can ask, like what are the relative height of each columns and so on. So if we have to build something to play this game, then one way to do this is to build some handcrafted features. Okay, and how does this handcrafted feature comes? Using some experience, let's say. It may be based on some intelligence of some expert. So there is an expert and to whom you can go and ask and learn from the experience that what do you think is important when you play this game, and then the expert might tell you that these are the things they look at when they want to play this game. So based on that, you may create these handcrafted features. So all these insights and experience can help you make these handcrafted features. Obviously, one has to ask whether the features that you have is good enough to completely solve this problem, or there is something missing in your feature, and that will have consequence on how you program this. What are the other systematic ways or automated ways to construct features? Like here we are saying, okay, we are looking at the gaps, we are looking at the relative height of the columns and so on. But is there a way to automate these features selection, right? So there are systematic ways to construct features. For example, use data and neural networks, right? And that is something we know from machine learning class. Is in the old classical vision problem, then you have a flower detector. Then they used to apply some hand crafted filters. They were handcrafted filters that used to be applied, and it was different for different problems. When they were doing texture analysis, there were other type of filters. When they were doing flower, there were other type of filters. Those were handcrafted filters. Just like the handcrafted features, here we are talking about portrait race, like where the holes, where are the relative height of the columns, and so on. In the earlier computer vision, they were doing this. But when neural networks came in pictures, and especially CNN, then it got automated. Now what CNN does is it goes through, it applies the filters on its own, and these filter weights are not fixed by hand. We let it learn what is useful as a feature. So that way, whatever the weights get updated will be a useful feature for CNN, especially if you look at the last few layers. Then the last hidden layer, let's say if it's a 10-dimensional one, then this learns some useful features, which is then used to predict whether it is a flower or not. Okay, so this extraction of the features happens by itself. Of course, here you need data. Here you need a lot of data to train such a network so that it learns to extract useful features. On the other hand, if you have something handcrafted, you are very knowledgeable with the features, then that is essentially a one-shot way. You don't need to train, because you built a filter by your own that detects the flower based on the features. Okay. Whereas if we have to use CNN, we have to first train it to learn to extract features, and then it can predict. So if we want to build an algorithm to solve the Tetris game, and with an automated feature extraction, then we will use CNN. Okay, so there may be one assignment on that. So we will apply CNN on the Tetris at each state. At each state, feature extractor is there, which is CNN. This, whatever it learns, it may not make sense to us because it's CNN. It's not handcrafted features. So it may learn some features that will make no sense to us, because for us, what makes sense is the gaps, relative height of the column, and whatever. But what CNN networks learn to extract features, sometimes it doesn't make much sense to us, but those are useful features in that let's say in that manifold that it's trying to learn, in that manifold of flowers. Whatever basis of these features are nothing but basis for CNN. So whatever these basis vectors that it learns, those are useful. They may not be useful for us, but CNN knows what are the good features to extract. So a state-of-the-art way to solve many problems is to use now some neural networks to extract features by itself, provided you have enough data, enough good useful data to give it to the neural network. Because if you don't have a good data to give it to neural network, the feature extracted will be bad. So how you generate data is as important as using automating this feature extracted. So this is one way. So as we know, just recall feature extraction from images. We see a bike. Maybe the important features are the wheels or the color and things like that. Okay. So in general, many problems could be seen as images, because even in sequential decision making problems, many problems, for example, robots can see, because there is a camera for the robot can see, and robot can extract useful features from whatever it sees. Okay. So then, and typically these are images, and so you need a feature extractor from images. If it's a chess game, again you take the image of the chessboard and let the CNN extract features for you. It will not only understand the state of your game from the picture, but it will also understand the current situation you are in the game, strategic things to do. So those are all the features that it will kind of try to most useful features it needs, it will try to extract. So let's say we have these features extracted, whether it's a neural network features or whether it's a handcrafted features, it doesn't matter. We take those features phi k xk. So feature extracted at state xk is phi k xk. Now we can go for these linear combination of these features. So basically these features becomes our basis vector, and using these basis vectors we construct our function approximator. So this is a linear combination of the basis vectors. So we can also write this as R transpose the feature vector. Okay. So the notations are kind of evident. So these R Lk and phi Lk are the Lth component of the weight vectors Rk and the feature vector phi k. So this is the diagram of feature-based architecture, where we given a state x, we do a feature extraction, we get a feature vector, and then we do a linear mapping. This feature extraction happens via neural network, or you do it by hand. So either you do it by neural network or by hand. That's it. And then you do some linear mapping. Okay, so then you get R transpose phi x. So that is all. So we can now, what are other ways you can try to do approximations? Then one possibility is if you define your features as a piecewise constant approximations. So we can divide our state space into m components like so. It's not always possible to do this. I mean, it's not always a good idea to do this maybe, but let's say if you can do that, then you can say that whenever x is in one of the subsets of the state space SL, then it is all 1 for that. So there can be many x which are in SL. So for all that you can say it's 1, or otherwise it is 0. Okay, so if x is in SL, then it's 1, otherwise 0. So then you can build a function approximation like this. So this is again a cost approximation. So this is the cost approximation we are talking about. This is done via piecewise constant approximations. So basically, out of all the features that you have, you are looking at which of the features are the most important. You are picking those, and that's how you will, and maybe other features will be given very less weights and so on. And this phi L is like a stepwise function here. Okay, so yeah.
So when we say it's 1 and 0, either it will be given an importance or it will be neglected completely.
Yes.
It's more like lasso, sorry, the regression feature selection.
Mm-hmm.
And in the previous neural network, we have a linear combination of features.
Mm-hmm.
Is that the difference?
Yeah, here it's about like we are just approximating it with piecewise constant. So these are the piecewise approximations that you have. Okay, so rather than saying that, let me give you some, like, let's say piecewise polynomial, then it could be like something like this. Okay, if I have a polynomial basis, then I do allow that, but then here it's like completely flat. RL is giving you the height, but otherwise it's ones or zeros. Okay, because of RL, you are kind of trying to adjust this.
In what scenario there will be partition?
So let us say my function is, the function that I want to approximate is like this, right? Then you divide this into various subsets, right? So what this is doing, you divide this into various subsets. Now what is piecewise approximation here? It will be this. So this whole thing, let us make this once again. Yeah. So we divide this into various intervals. Our goal is to approximate J tilde, which is possibly nonlinear. So possibly nonlinear meaning this blue one is J tilde. And piecewise approximation of this is that from here to here, I approximate this function like this. From here to here, I approximate this only by constant. That's the thing. It's not even telling you that it's linear. It's just always flat. So here it's telling you this. Here it's giving you this. So this is the piecewise approximation for this example. Piecewise polynomial, if phi, so this is here, it's the class of functions that I'm allowed to is just constant, right? And I'm allowed to multiply that. So it's like a span of a constant. If you want to see this in a polynomial basis, so this will be treated as J tilde coming from some span of constants. Okay, our constant is like, let's say 1 of these, right? But here the important thing to note is like this is kind of here we have a partition of the state space. So it's not like uniformly it's a span of these. It's a span of this one in set S1. It is span of one in S2. So it's like depending on the region where the state is. So it's like in an interval it's a span of a constant. A span of constant, like the constant times the basically it's a constant. And another region it takes a constant but some other constant. So depending on the state, it will take different values. So this phi equals 0 or 1 is a basis only, right? But which is just a constant. So for if you see an x in SL, right, then you will say yes, I'm supposed to take the one value, but there is a r there. But r will tell how much. It's like here, if you see, if x is in SL, and let us say SL is this. If x is in SL, SL is this. So let us say x is somewhere here. Then I know that it's taking non-zero values. So here it will be multiplied by this phi r, corresponding r of phi Lx. Now this guy is 1. Now everything depends on r, like how much this r will take. That will tell you where it's approximating the function, how high it should be to approximate the function, right? And you can do it in 2D. It's not necessarily a 1D, right? We can think of a 2D example where we have a cost function here, and we will divide this into these small planes, and the basis function will be defined for this region. Okay, so let us say this is our phi L. So this is our phi L. Now your basis function is a small planes. Okay, so these are small planes. So now it will it will approximate this patch area here, and then if it comes here, it will approximate by a small plane here. So that way this will be piecewise approximated. So this is, so you can approximate any high dimensional problem also. It's just that it has to be linear. So linear function in a 2D is a plane, linear, or let's say affine, right? So it's a constant basically, but it's a constant throughout in a patch of the plane. So we can do this, and it's very cheap basically. So that's why computationally it will be very cheap, because this is like phi L is like either 1 or 0. So basically you are optimizing over R. So R is the parameter of this model that you are supposed to find out from the data itself. Okay, so that's it. So these are like part of the numerical thing and numerical algorithms. How you do piecewise approximation as a basis, you do polynomial basis, you do wavelets, Fourier basis, sine, cosines, and there are like so many range of things to do here. Okay, in fact sometimes you write paper just on this. You say, let me try some interesting approximation, and in the paper you can say this, I proposed a cheaper approximation which gives me same accuracy. You can say that. Like, it's not necessary that you use neural network all the time. Sometimes you can say that, look, I propose this nice interesting approximation. So there are books written on this numerical approximation. So you can pick some interesting idea from there and say, look, I propose this approximation scheme, and this helps, and this is faster, cheaper, whatever. So you can go into like Gaussian basis functions, things like that, like kernels that you see in machine learning. So the type of kernels that they use, right? So so all kind of things could be done, right? So so there is whole range of possibilities here to try. We are only looking into some of them. The polynomial features, so that's like pretty obvious to discuss. So we saw ones and zeros, which are like a very special case, piecewise constant. But now you can go generalize a little bit. And so what are polynomial features? As I said, polynomial features are these 1 or these x to the I, or you can also mix these features. Okay, so if your state contains n components, then many types of features you can construct. Just like if you do in kernels in SVM, you have those polynomial kernels. You can construct as many features as you want, depending on. So most general way to construct these features could be, let's say, up to 2 degree. So you mix xi xj. So that gives you like one possibility, like this. The way notation is written is these components are like this, right? So the components are like this. So these are actually components, n components. So these are kind of like linear combination of these n components, right? So these are not the powers of x, right? So these are components. So first component, second component, third component, and n components. And these are linear combination of these n components. And then there are mixture of these components, so product of these components, x1 with x2, and x1 square is also there because I equal to j is allowed. So x1 square is there, x1, x3 is there, and so on. x2 square is there, and so on. But yeah, so but only up to squares it's allowed. Okay, the sum of the degrees is 2. So these are your features. So as you can see, the feature space is quite big here. So these are, let's say, the feature of x at the state x. Now it's about doing a linear combination of these features. Okay, so in this case, if we look at the number of features, we had 1 plus n squared. So we had so many features. Feature space dimension is like n squared plus n plus 1, and so this is of that type. And then we have linear combination of this. As you can see, it's a linear combination, right? Because so everything could be written as some vector r. So these r, you collect this, and then multiply. So this is a transpose of these features that I talked about. X1, X2, 1 is also there, and so on. X1, X2, and so on. So basically, this is a linear combination of features. Okay, and so this is seen as a linear because it uses these as a basis that I just explained. So features can be guessed in Tetris game. So if you see the papers, original papers of the Tetris game, then these were the features considered. So they considered the heights. So these are handcrafted features. Okay, this is not by any neural network or something, right? So this is wall height, number of holes in the board, and then constant 1 was added, as you do typically in classical machine learning. You add 1 for the bias. So these were the papers that use these handcrafted features to create an algorithm that can play Tetris game, and they could do this on a very large state space. Can we extract features for chess? As it turns out, chess is slightly more involved than the Tetris game, because chess has more possibilities of strategies. The possibilities of look ahead and the length of these multi-step look ahead is like really big compared to many other games. Chess is way more complex. So obviously we have seen some computer engines to play chess, and they involve some features. Okay, there are obviously the earlier ones were all kind of handcrafted features. Okay, so they were expert players. They used to tell that, look, this is what I feel is an important features, and based on that they used to make these computer engines. So obviously now we can use neural networks in these cases. Okay, so this was a brief history of Kasparov, where for the first time a world champion was beaten by a computer which is called IBM Deep Blue.
Grandmasters had coached IBM's programmers to deepen Deep Blue's book, its library of what humans knew from experience about how to win. Deep Blue could now play as well as a grandmaster, with all the benefits of hindsight. In the early moves of Game 6, playing by its book of openings, then in the mid-game analyzing millions of possible scenarios by sheer brute force, Deep Blue has led Kasparov into making a poor move. Kasparov is rattled. He defends what he can, but it's clear that the computer will reliably do what he himself would do. And he recognizes that he has already lost. On Deep Blue's 19th move, the champion resigns. Nevertheless, the machine they had built did not play chess by thinking in the same way a human does. A machine that can think remains the dream, and it's still many years and quite a few startling breakthroughs away.
And this was in 1996, where IBM Deep Blue lost once, but Kasparov won, I think, the remaining 2. But then they did this again. They came with this updated software, and then the software won 3 times, and it lost 2 times. So a lot has been done since then, since 1987. Now we have very powerful chess players, and one of them is AlphaZero. What is interesting about these is like they are fully automated. In fact, apparently the word zero means that it can learn from scratch. You don't even have to teach the rules. It will just watch the game, what happens in the game, and what is the final reward, who wins, who loses. It has these neural networks which extract the features, whatever is important. It learns the rules of the game and how to play the game also. So this was a fully automated way, and now no one can beat AlphaZero. Almost no one. Like by chance you may win. 1 in 1,000 chance you may win, but in general no one can beat this. They are so powerful now. So but what were the features extracted for chess? We can start with the handcrafted ones. So maybe this might go into a small assignment as well, where you might implement this use these handcrafted features. So obviously we know, like, who else? The guy who so here, this is Shannon, right? Yeah. So this is Shannon. Bellman also proposed some handcrafted features, and then we had Shannon, who wrote this information theory article. So it's kind of like was a big breakthrough in that area. So these chess programs were based on approximate DP for minimax problem. It's a minimax problem because there is an opponent here. Now we will go into minimax in the second half, which will be a lot more fun. After mid-sem, we will look into this minimax problems and multi-agent, and that creates a lot more complexity. So whatever we have done so far is a base for doing more complex problems. So chess could be seen as a minimax because a player is kind of trying to maximize their reward, and then there is an opponent who is trying to decrease your reward. So hence it becomes a min-max problem. However, if you go by a game theoretic approach, still it's a very hard problem to solve. And it is a sequential division problem again. So it is a min-max but not simultaneous min-max. Simultaneous min-max have Nash equilibrium, whereas we are in the framework of sequential min-max. So a player will do something, then the other player will do something. So it happens in a sequence. Okay, so there are two classes of min-max problems. One is simultaneous, one is the sequential. Okay, so earlier results on this was by Shannon in 1950. So Shannon proposed a multi-step look-ahead approach. So we know by now what could be a multi-step look-ahead. And he also, because in this case you also are kind of supposed to come up with some way to evaluate. So basically the cost function, what could be a cost functions, how should we evaluate that cost function in a chess game, right? So and evaluations of the end positions by means of a scoring function, which we can call this as cost function approximation. So he proposed this in this paper. Maybe you can do this assignment a bit on this based on this idea. So this scoring function obviously includes numerical values for the major features of a position that the chess players may recognize. So it involves, let's say, material balance, like how many pieces you have, how many pieces opponent have. So this could be an interesting features to capture. So we can call this material balance as a features. Mobility, how much mobility your pieces have, how constrained your pieces are in the chess game, where is the rook, how much it can move, and bishop, and so on. So we will look into these in detail a bit later. I guess we are supposed to wrap up. So and then pawn structure, like how are your pawns spread out, and other positional factors. So we will get into a bit more detail of this work. And based on this, he defined this cost function, which basically gives a numerical value. So this is cost approximations. Okay, based on whatever features we have, how can you approximate the cost? In this case, the cost is like the reward, whether you're winning or losing, let's say. Okay, so he did this by hand, basically. So by hand we mean like he has to identify these features by hand, rather than doing it in an automated way like AlphaZero. So Shannon also described various strategies for exhaustive and selective search over a multi-step look ahead. So these are the things he already considered in 1950s. What are the selective ways to search, or the prioritized way? Are there any priorities to be given to certain actions which should be taken a lot more than the uniform sampling or whatever, right? So he did some of these ideas. And then so in general, like in most chess games, we will have these features. We will do this linear combination of these features, and we will build these approximation functions, and we do multi-step look ahead. So all this gets combined very nicely, whatever we have studied so far. So the recent breakthrough comes from extraction of features through let's say human expertise, or let's say via self-play. So you play a lot of times and then you see by yourself if it gave good reward, then kind of that's a good set of actions to take, and you collect all this data in a nice way, and then you build this approximation architecture. So I have already said about Alpha 0, and it's a DP principle and multi-step look ahead, and also uses Monte Carlo research. Okay, so I guess I will stop here. The best thing is to understand is like there are cheaper ones like piecewise constant. If you can get away with, it's the best. Go for polynomial approximations, or if you can generate a lot of data, then go for neural network based feature extractor, which works very well for very complex and very high dimensional problems. Okay, so we will stop here. So we will try to release assignment on Tetris game, where these feature extraction and all this you will see, implement, and see for yourself how it can learn to play the Tetris game. You will do look ahead steps and so on, and then I'm not completely sure right now about chess. I will try to create one assignment for chess as well. Okay, so once you actually implement this, you learn more, because mathematically there is not much to say. It's more about putting things in place, how the feature extractor works and so on, how do you train it, and so on. So if you implement, then you will learn a lot. Okay, so with this we will stop here.